Today I'll presenting our paper, DISTMM, Accelerating Distributed Multimodal Training. And my name is Jun Huang. I'm from The Ohio State University. This work is done during my internship at AWS, and many thanks to my collaborators. So in the timeline of large model invention, in 2023, most of the models are LLMs. There are only 2 models that are multimodal models. But in 2024, things have changed. So most of the models are multimodal models. Multimodal models are more powerful than LLMs by being able to integrate information from multimodal information. But when we train the multimodal models, our experience is that the training process suffers from low GPU utilization. And this low GPU utilization problem actually has a pattern. That is, the low utilization operations are often associated with certain modalities instead of all modalities. However, training a unimodal model with the same training system will not suffer from the same problem. And we will talk about the reason later. And besides the utilization problems, the most critical problem is existing pipeline parallelism is not compatible with multimodal model training, which makes the development for a large multimodal model difficult. Because pipeline parallelism is an essential technique for scaling up the model size and scaling out the cluster size. So we propose DISTMM, and our goal is very clear. The first goal is to train multimodal model as efficient as training unimodal models, because unimodal model training nowadays are highly optimized with acceptable utilization. So our goal is to have acceptable utilization. And the second goal is we want to support multimodal model training with pipeline parallelism, because we want to make sure the development of multimodal model to be easy. So this is the model structure of a general multimodal models. So we can understand and generate input and output from different modalities. And for each modality, it has its own encoder and decoders. But the core of multimodal model is the modality interaction modules. And the input to the modality interaction module is the feature vectors in unified representation space. It means the feature vector has to be projected into a unified space. This is the only way they can combine and interacting with each other in order to accomplish the multimodal task. So the goal of training a multimodal model can be divided into 2 categories. The first category is the same as training a unimodal model. That is to make sure the model can better understand and generate unimodal information. So this is the foundation to multimodal task. And the second goal is to ensure the multimodal information can be aligned. And the goal is to learn a better unified representation in order for them to interacting. And the method is to use contrastive learning, which is very intuitive. So during contrastive learning, if we have a positive pair, which is the image and the text correspond to the same object. Right now in the example is a picture of a dog and the text of a dog. So after the process of encoders, the feature vector should be the same because they correspond to the same object. So contrastive learning will maximize similarity. While for negative pairs, contrastive learning will try to minimize the similarity. So this is where the 2 categories of learning happens. The constructive learning happens on the unified representation, so decoder will not be involved. And we want to talk about the reasons of the low utilization problem. So here is the example of a typical matrix multiplication. So it can be described into 3 dimensions, M dimension, K dimension, and N dimension. And these 3 dimensions is associated with the utilization of the matrix multiplication. The larger the better, because the larger the multiplication usually means higher efficient kernel. And it can also help to hide the memory movement overhead. And this is a typical linear operation used in model training. And this is how the 3 dimension is associated with the hyperparameter of the model training. So here we'll talk about the difference between the modality, which is the reason why the utilization is so low. So we use clip model as an example. The clip model takes image and its caption as an input. But the caption is usually short, so the sequence length for the test input is only 77 words. But for the image input, the sequence is 256 patches. So these varied sequence lengths contribute to the utilization differences for the test submodule and vision submodule through the M dimension. And since clip model is image retrieval models, so it actually has a focus on the image encoder. It actually required a larger image encoder compared to the test encoders. So for image encoder, it has a higher hidden dimension than the test encoders. And these varied module size contribute to the utilization through K dimension or N dimension. But between the model differences and the utilization difference, there's a middle layer, which is how we distribute the models. And for data parallelisms, the M dimension will be further partitioned into the size of the data parallelism. And for tensor parallelisms, the K dimension or N dimension will be further partitioned. For hybrid parallelisms, the M for the smaller module with shorter sequence length, it has to be partitioned on M dimension. But we can see after the hybrid parallelism, the M dimensions difference is enlarged. So this is not expected. So we conclude that the DP and TP solution as co-locate solution, because on each device, all of the submodules will be either replicated or partitioned. So in conclusion, the drawback of the co-locate solution is it treats the smaller module or the module with shorter sequence length unfairly, because in reality, the smaller module or module with short sequence length should be partitioned or replicated less. This is the only way to avoid overhead. And second, for the co-locate solution, there will be memory overhead in storing the model replication of the smaller model. So this is why the utilization is so low. And the second differences between multimodal model and unimodal model is that is interaction within batch, while unimodal model does not have. So it's the same to run 100 batch size 1 forward step for unimodal model training, and it's the same with running 1 batch size 100 forward step in unimodal training. It's equivalent, but it will not be equivalent in multimodal training. And this is how we vectorize the simulated matrix. This is how we vectorize the constructive learning in a simulated matrix. And by constructing this simulated matrix, we can see in the diagonals, there's the similarity of positive pair. And for the element not in the diagonals, there's similarity for the negative pairs. And the scale of the simulated matrix is important for learning a robust unified representation, because it can lead to a model with higher model qualities. And in the real life scenario actually requires a batch size larger than 10,000 to guarantee the model quality. So pipeline parallelism is not incompatible with multimodal training. That is because pipeline parallelism requires to divide a global batch into multiple micro batches. We can see from the example. For each micro batch, you can only generate a very small simulated matrix. But what we expected is a large simulated matrix that takes all available memories. So you can see during training, if we use pipeline parallelism, there will be a lot of information not near the diagonal are missing. So pipeline parallelism can actually result in a model with lower model qualities. But in reality, the batch size is actually provided by machine learning engineers. So for example, they just give you a batch size of 10,000 because they want the model to have a higher model qualities. So if pipeline parallelism can actually achieve this 10,000 base size, by scaling out, it will still be useful. It will still be usable. But our formulation here shows the maximum base size is bounded by a fixed value and is not grow linearly with the pipeline stages. It means the upper bound shows the available memory is limited to a single GPUs, which is unacceptable because 10,000 base size actually requires the memory of multiple computation nodes. So we propose DISTMM. So we have 4 system components, and the first 3 components is to ensure non-collocate solution. And the last component is pipeline parallelism with linearly increased base size. And the first component does the adaptive partitioning, so smaller module can be partitioned less, while the larger module can be partitioned more. And the second component ensures the partitions to be load balanced, so there will not be overhead. And the third component ensures the non-collocate placement, so it can avoid some communication. And the last component ensures the pipeline parallelism with linearly increased base size. So this is the example of our first component. So after adaptively partition the model based on the memory consumptions, we can see the k dimension and the n dimension are more similar. It will result overall high utilization because the smaller module now has a similar utilization comparing to the large modules. And for our data load balancer, it means to balance the m dimension. So the smaller modules with shorter sequence lengths now will have higher sequence lengths compared to the large modules. And it can also reduce the memory overhead because this is a non-collocate solution. And this is our third component. It can reduce the gradient synchronization communication because in our solution, the computation is similar or the same during load balancing, while the communication is reduced from 2 submodules gradient synchronization communication to 1 submodules gradient synchronization. And for our last component, we propose a batch sync instruction, which will concatenate the feature vectors of our previous forward steps in order to compute a full similarity matrix and dispatch the gradient in order to launch backward computation. But we can see from the example here, there will be a conflict because the dispatch actually happened before the concatenate. So this is violate our goal. That is, we want the schedule that is as efficient as the 1F1B schedule. So we designed a pipeline schedule called DISTMM pipe that is divide the microbatch into 2 and create 2 pipeline flows. The first flows will go through the batch sync instruction in order to calculate a full symmetry matrix. Then during dispatching, the second pipeline flow will be launched and inserted into the dispatching. So it conforms a perfect 1F1B schedule, which will ensure a minimum pipeline bubbles. And through our formulation to the batch size, we can see the batch size for DISTMM pipe can linearly scaled with the number of pipeline stages, which means it can achieve any requirement for the batch size. And this is our evaluation for DISTMM. So we choose image and text as the 2 modalities, and we choose 3 models with different structures. So for clip models, it requires a larger image encoder, and for COCA, you require a similar text encoder with image encoders. And for LID, you actually require a larger text encoders. And we further scale the models into 3 scales to test the scalability of our systems. And we actually compared our system with Megatron LM, and we use the best configuration of Megatron LM towards each models. And this is the overall performance. You can see DISTMM actually have speed up over Megatron on every configuration. And the speed up actually increases with the batch size, with the model size. Because for single GPU scaled models, they only suffer from sequence length differences, but for single node models, they additionally suffer from the over-partitioning. And especially for the multi-node scale models, since Megatron LLM's pipeline parallelism cannot be applied, so it can only use cross-node tensor parallelism. But for DISTMM, we can use pipeline parallelism to speed up our process. So this is why the 3 times speed up comes from. And this is our breakdown to each submodules. So in this case, we only use additive partitioning for the single node models to see how the utilization of each submodule will be like. And we can see the smaller modules has the highest utilization improvement due to the avoid of over-partitioning. And for single GPU models, we only apply load balancing to it to see how the utilization will look like. And we can see for the module with shorter sequence length, it has the highest utilization improvement. And this is because before the load balancing, the smaller module only takes a smaller fraction of the whole GPU memory, but after load balancing, you can take up the whole GPU's memory. It means a larger batch size. And this is the conclusion. So DISTMM only works because we take advantage of the unique parallelism opportunity of multimodal models. That is, the submodule can be executed in parallel, and it has a very highly parallelized modality interaction computation. And we have advantage over computation, communication, and training accuracy. And this is all. Thanks everyone for listening. I can answer very long.